Welcome to this session where we're honored to introduce Gregg Bartlett, the Chief Technology Officer of GlobalFoundries. They're a major force in the semiconductor industry, employing over 13,000 people across multiple global locations. As one of the largest semiconductor manufacturers in the world, the company is key in producing cutting-edge technologies that power everything from smartphones and IoT devices to advanced computing systems. Gregg Bartlett brings over 30 years of industry experience, having previously held senior leadership roles at Motorola and Freescale. He serves on the Industrial Advisory Committee in support of the US CHIPS and Science Act. Under his technical leadership at GlobalFoundries, the company has made significant advancements in both photonics and semiconductor technology, anchoring a position at the forefront of global innovation.
Good afternoon, everybody. Jose, thank you for the opportunity to talk about GlobalFoundries, but more importantly, about 6 or so weeks ago, you held a prep session for the energetic panel that we had yesterday. And I got so wrapped up in this is silicon photonics, a semiconductor technology, juxtaposed against this being an economic forum, that I actually said I'm going to dedicate my entire presentation to it. So, you see the title of the talk is around solving the economic equation for silicon photonics. Before I do that, this is obviously my first trip to Malaga, first opportunity to meet a lot of the European audience that's here. To the organizers and coordinators of this event, really, really well done. Congratulations. It's a pleasure, and I hope we get invited back next year. So I probably should update my bio. I'm in my 41st year in the semiconductor business, so I'm declaring my bias up front about the lens by which I look through silicon photonics. In fact, that lens for me started when I moved out of one of the product lines that I had been running. I started as CTO. For 4 years, I ran a product line and then have been back in the CTO world for about 4 years. And 4 years ago, I stuck my head into this window called silicon photonics and said, what is going on in here? And that's the context by which I'm going to walk through the presentation today. So a brief introduction to us. We're a $7 billion plus semiconductor foundry with our largest facilities in Singapore, where we have about 8,000 employees. Our largest single factory is in Dresden, Germany, that has been expanding for the better part of the last 5 years. We have a facility in Burlington, Vermont, and then where our silicon photonics technology is developed and manufactured today is in our upstate New York, just north of Albany. And I wanted to start with this slide because it shows the 4 product lines and 8 significant technology platforms. And the significance of silicon photonics being one of those is one of the core points that I tried to make on the panel yesterday, and you'll hear from me again today, which is the benefits of silicon photonics seeing 7 other technology platforms, manufacturing capabilities around the world, is the core value proposition to what we can bring to the photonics industry. Bring that semiconductor mindset to a pretty immature technology and industry at this point. So I want to frame a couple things around why we see silicon photonics as an attractive market. First and foremost, it's physics. We ultimately know that copper and electrons are going to hit a wall. You'll see that in a minute. Secondly, and you see a chart here, the trade winds in the last few years have become very favorable to adoption of silicon photonics. A couple charts from Hot Chips, this one showing going to 100 trillion parameter models and the amount of energy it takes. So suffice to say that silicon photonics has a lot of tailwind there. Same thing when you look at the interconnectedness within the data center, where today you see this incredibly complex interconnection in the data centers of every GPU having direct access through optical connections to every other GPU on there. So really favorable aspect of it. But let me create the drama or the problem to be solved in the presentation. We do know that, first and foremost, photonic technology has historically been in the realm of long-haul communications, And even in the electrical world, there's this interconnect wall. And this is a slide that I stole from Joris at our dear partner IMEC that's been a really, really key partner for us in this journey. And it benchmarks all the electrical and optical performance that's there. So how do you break through that interconnect wall? Well, we believe silicon photonics is going to play an essential role. And that little point that just appeared on the screen was Air Labs' demonstration of a 4 terabyte frequency performance running about a year ago. I think it showed up at OFC in 23, and it made the rounds. And it was the first data point over the wall. And you'll also see that it's down in the electrical domain. The roadmap we're on is, in fact, through innovation in the development of the technology, and I've oversimplified this chart because you can separate pluggables from co-package optics and the interconnect distance, so that blue box is probably 2 of them, but I've simplified for the purpose of this, where we do see the development of this platform being critical to both improved bandwidth performance in pluggables as well as a essential role in co-package optics. So in the briefing for the panel we had yesterday, Jose asked the provocative question, but is it really ready for prime time? Are we really ready for this revolution where silicon photonics is ready to take off? And it caused me to do a little bit of reflection, and I said, well, to be honest with you, I think there are some inconvenient truths associated with where the silicon photonics readiness for broad adoption in the industry. And let me walk through them. I'll use Matt Crowley's comment from yesterday about technological diversity. He used the word snowflake. And in fact, we feel like that, where every single customer has their own unique approach to what they're doing. And the technological diversity is actually expanding rather than standardizing. I'll talk about what we're doing to mitigate that. But we have between 250 micron fiber, 127 micron fiber, silicon waveguides, silicon nitride waveguides, germanium photodetectors, Mach-Zehnder interferometers, micro-ring resonators. It is a zoological garden of components that are going into these devices, all of which need to be qualified, proven for performance, et cetera. So a big part of our strategy is convergence here. The second one is, and this is maybe a statement still at the data center level, but the MTBF of these really large interconnected data centers is not measured in years. Matter of fact, it's probably measured in days or even in hours, given the complexity of there. So reliability of the components we supply into there is a really critical foundation. And it's been a journey for us over the last 5 years, getting us to have confidence that every exploitation of the optical components that goes into one of these chips is reliable through temperature cycling and damp heat and things that I'll talk about in a minute. And then, as you heard in the panel between Ashkan and I yesterday, I am a firm believer in the learning curve. And Moore's Law is, quite frankly, nothing but a statement of the learning curve that says by you practicing things at very high volume, you learn how to take cost, you learn how to miniaturize on there. We know that silicon photonics will ramp, will follow the same learning curve that the other 7 technology platforms that you've seen go through. Now, to be clear, GlobalFoundries, we abandoned the bleeding edge of semiconductor technology at 12 nanometer. It got too rich for us to spend $3 billion a year on a 3 nanometer FinFET technology. That is not to say that the things we do of embedding silicon germanium into a logic process or embedded non-volatile memories doesn't follow its own learning curve. So we've seen this over and over and over again, and it's why me, as a 41-year semiconductor technologist, believe that we need volume drivers that are going to adopt this and drive us to the cost and throughput optimization that has to have. Matt showed a number yesterday of putting in just the metallization line for silicon photonics being a $250 million investment. In a minute, I'll show you how much we've already spent just on the wafer processing. And then real or perceived, there is a fundamental belief, and I'll show you some cost models in a minute, that today the cost crossover on an equivalent level of performance is not there. So that chart on the interconnect wall, I didn't highlight the key figure of merit, but it was gigabits per second, per millimeter, per picojoule per bit. So it's a relatively esoteric figure of merit, but it actually captures power, coupling distance, and bandwidth in a single metric on there. And we do believe that today the cost probably isn't there, but that there is a roadmap to get there, which hinges on a high volume driver, standardization, et cetera. And then, I was talking to the CTO of one of our major customers at a conference about a year ago, and he looked me in the eye and said, Greg, I don't think you understand. The single thing holding up the adoption of silicon photonics is there is no packaging ecosystem in the industry for it. The traditional OSATs are still waiting for the first 3 million units per year to be able to make the investments, and they have no experience in handling optics in a manufacturing and assembly line. You start talking to them about polarized maintaining fibers in there, and you just get these blank stares on there. So it is a big gap, and it was really about that time frame where we said, wow, we're not just going to be selling a wafer into a fabless circuit design company. We need to go make the ecosystem work. So, quite a few uncomfortable economic truths associated with it. So what do we do about it? Well, the answer is to make photonics product and manufacturing to look as much like semiconductor products and manufacturing as you can. Meaning that you're leveraging the refinement and accuracy of the tooling that you use in your 300 millimeter factory, the precision of the lithography capabilities on there to be able to control the shape and form factor of the germanium photodiode, and certainly the level of automation, right? If you go into our factory in upstate New York, it's a lights-out factory. You see equipment technicians in there performing maintenance. You don't see operators. Everything is fully automated from a time a box of wafers goes into the line to the time they come out. It never gets touched by a human hand. It literally never gets touched by a human hand. So that's the premise. But I'll tell you, one of the hard lessons learned is appreciate where CMOS technology or any semiconductor technology isn't compatible with optics, and ignore that at your peril. And there are a lot of things that we have learned painfully, whether it's device performance and integration challenges or reliability, where in fact optics does not look like it. So it's key to leverage it, but know where they differ. Okay, so how do you do that? In the next few pages, I'm going to unpack 6 ways we are working to solve this economic challenge. The first one starts out with doing what semiconductor foundries do. When Morris Chang invented the industry 40 years ago, it was because technology and factories were getting expensive, and no IDM had the financial investment capacity and large enough demand to warrant the level of investment. So he said, I'm going to consolidate demand. And 40 years later, the industry continues to thrive on making standardized platforms available. For us, we took a 45 nanometer logic and RF technology and worked to make a monolithic, meaning that we've integrated all of the optical elements that are necessary for a silicon photonic device to be monolithically integrated. It is an extremely challenging thing. One of the reasons learning cycles are long is the mass count for this process is pretty significant. And you might ask why. Lots of folks do PICs and EICs separately and use micro bumps to interconnect them, or ultimately TSVs in there. Well, we wanted to start with a foundation that says when a LiDAR guy comes to us or a biosensor guy comes to us and they need CMOS logic integrated, we've already done the hard, heavy lifting in that platform to be able to have the monolithic integration. Do we support PIC only? Absolutely. It takes out a bunch of mass and a bunch of complexity on there. So we've got this, first and foremost, the foundation. So in the orange boxes, you see the CMOS-related features that go into it. And there's 2 things we did. Took a very stable 45 nanometer logic platform, and importantly, we were already doing a millimeter wave frequency performance in the aerospace and defense space on our 45 nanometer in an RF SOI instance, and we took a lot of that learning and knowledge to make sure we had good FT performance on that platform. In the blue outline boxes, you see what I refer to as the zoological garden of all the different optical components that you have to put in there. Mach-Zehnder interferometers, micro-ring resonators, ring-assisted Mach-Zehnder interferometers, the germanium photodiode, and then all forms of manipulation, steering, and modulation of beams of light. In the bottom, you actually see both the ability to integrate a laser on board. It's a metallurgical solution with a large laser cavity that we carve into the device. And then, probably one of the most difficult solutions is how you get fibers in and out. And in yesterday's panel, I gave the C4 analogy. Nobody thinks about tin silver bumps or copper pillars in the electronics side of the industry. It is one of the most devilish aspects of getting fibers in and out, and the rate and pace at which fiber count scales really puts some challenges on there. In a bit, I'll talk about some of the form factor challenges as co-packaged optics comes into it as well. So for those of you in the back, you probably can't see it, so I'll call it out. But on the bottom of this chart, it shows that we've spent, just on this photonics platform, already over $300 million, and I tell you, it's significantly over $300 million. So it is not for the faint of heart. And as you heard from Matt yesterday, this is just the fab portion. It takes another $250 million to put the infrastructure in place. So fortunately, we have had a very patient board of directors that has allowed us to invest for the long term on this platform and go build it out in the right way. Okay, so first of all, have a platform, drive everybody to it, say no an uncomfortable number of times when people come in with their Baskin's 31 flavors of different things that they have ideas on how they can make the most differentiated photonic product that exists. And we've said no a lot. We have this qualified platform. Please use the components that are here. I would say that it's a little better than a stalemate, but we do wind up having to entertain still a massive amount of diversity on there. So as you then think, what's the next thing you need? Well, a roadmap. And you see some of the things that you have to address in the roadmap. The fact that bandwidth is going up 2x every 2 years, all the while being pushed to get down to 1 picojoule per bit or below. Photonic architectures, today the vast majority of the engagements we have are, single lambda per fiber implementations. We know we have multiple tapeouts on CWDM, and of course Air Labs started with us on DWDM several years ago. All the while those things you're doing, you also need to get from 100 gigabit per second to 200 gigabit per second for the optical operating frequency in the devices. Pluggables, I mentioned. So we started out with this really cool V-groove process where we can passively align the fibers into the die, and it's a wonderful pluggable solution. But as soon as you want to take an optical module and put it onto a laminate substrate, 6 inches by 4 inches, you quickly realize that the HBM memory and GPU on the other end of that thing is $40,000 worth of materials, and you have this relatively modest optical module that you're putting in there. And the last thing they want to do is trying to run that thing through an assembly process with these fiber optic pigtails hanging off these optical modules. It doesn't work. So it drives you to have to do wafer-level detachable fibers, and it significantly complicates the assembly process. And then the last thing, you got the impression from the interconnectedness of the data centers now, we do know that for the resilience and ability to move compute loads around one of these superpods with 32 racks of thousands of GPUs in it, optical circuit switching is going to see its entry into that space. Optical circuit switching requires very, very fast switching capability and low latency on there. For us, that's going to introduce new materials, whether it's thin film lithium niobate, barium titanate. So there's a lot of things you have to think about when you're putting together a long-range roadmap. And I should have given you the caveat. There's a CTO making an economically oriented presentation, but he's still going to show some technical data. So this is the work we're doing on enabling 200 gigabit per second. There's 3 things you got to get right in processing light in a silicon photonics product. Detect it, modulate it, and steer it. Right? And that sounds pretty darn simple, but it turns out that there's a lot of details that go into it. On the left-hand chart, you actually see so today we have a 35 gigahertz bandwidth in our germanium photodetector. We know that we need to have better than 60 gigahertz to be able to enable 200 gigabit per second. This already shows data at 65 to 75 gigahertz of performance at 2 milliwatt input power into each one of the photodiodes. So we're ready with the germanium photodetector for 200 gig. The middle chart now is like, okay, well, you got to do the same thing and get your modulators to that level of performance as well. And you can see some of the metrics associated with insertion loss and bandwidth. And our ring-assisted Mach-Zehnder interferometers now at 60 gig and around 1.5 picojoules per bit for the solution on there. Not yet to the 1 level that we're driving towards, but very good progress towards enabling it. And then finally, steering light. And of course, there's polarizers, splitters, muxers, demuxers on there. But as you introduce CWDM, you have to have the ability to passively separate multiple wavelengths on there. So by using only silicon nitride, some very creative device layout optimization, you see the ability to have really, really good signal-to-noise representation for 4 lambda in the entering into the platform. The second thing you got to do is, well, if you're doing 4, then can you do 8, 16, 32, 64 on there? And we've been working with Air Labs for a number of years on there. But another really critical parameter enters into the equation, which is yield. You now have these fibers coming in with 8 lambda on them, and you need to split them up and steer them, modulate them, et cetera. And you have to have really high yields. So in addition to the frequency performance, you also need to get to good yields. If you look down the middle column here, you see that at 2 dB of insertion loss, we're at 99% yield, and even going to 200 gig spacing across the 8 lambda, you see that we're at about 98%. Not yet where we want to be, but really promising. The next thing you have to enable for the next couple of generations is, as I've already mentioned, the need to get to a wafer-level, optical testable, detachable fiber attach process. And those are the hard things. Well, there's actually even harder things. What we know for sure is active alignment of fibers to waveguides is not a long-term manufacturable process. It's why we started with our original V-groove that passively aligns it. That does not work for a co-package optic. So, today, the good news is we're reusing the laser cavity that we created 5 years ago for the integrated laser and are now putting a optical component at the wafer level that allows you to go through the entire 4 test insertions and all of the thermal cycling of the assembly process. And the very last thing you do when you have 8 optical modules sitting on a 4x6 laminate with GPUs and CPUs, you've already tested that those optical modules are known good, and you can click fibers onto each one of those optical modules, the very last thing to be done. And then, of course, yet another test insertion just to make sure that the coupling is there. The key to this is to enable it being passive. So the diagrams that you see below that cross-section actually represent a 1 dB window over a plus or minus 40 micron alignment accuracy on there. So it's a really, really robust window because inside the drawing you can't see are some expander and contracting mirrors that allow you to have pretty robust alignment when you bring that coupling device in. All right, so you have to have a roadmap. Well, then you have to be able to assure people that you can handle the commercial side of it. So three things that we've highlighted here. Since January of 2023, we have run 25 customer new product introductions, as well as the MPWs that we run through the line. And you can see that we're doing 1 or 2 a month in there. We're gating that simply because most of the tapeouts we get have still a lot of work to be done, or they've implemented features that weren't even supported in our PDK and they have to go re-engineer it. So there's more than 2x the demand for us, and we're working to do what we do in other parts of our business. So in the RFSOI, right, the diversity switches, tuners, LNAs, PAs that go into your cell phone, we have 5 driver customers, right? The Qorvos and Skyworks and Qualcomms and Broadcoms. We do 1 tape out a day for them, literally 30 a month. So we know it can be done, and we're looking at, okay, what does it take? You can do 1 a month here, and you can do 1 a day here. And that's actually the drive that we're doing, what level of automation for automatically generating, and certainly early engagement with the customers to make sure when they tape out that it's not a box of rocks. So NPI frequency and learning cycles is key. The second one is customer shipments. There's only one thing wrong with the up and to the right chart that you see there, that's an up and to the right for 12,000 wafers that we've shipped. Anybody looking at economy of scale in a semiconductor manufacturing facility know that that's about 1/10 of what you would like to run on an annual basis to be able to drive the same learning curve that has happened elsewhere. Hence my comments in the panel yesterday, volume matters, driver customers are going to show up and make that work. Then the third thing you have to have, of course, is good yields. And that's a statement about both the CMOS yields that go into the platform, which is a very, very mature technology, as well as the optical. And we're making very, very good progress. We still have more work to be done, and there's a lot of unique failure mechanisms depending upon the diversity of what customers are using. But you have to assure a customer that you have all these capabilities in place. So I go back to the library of electrical and optical components, and you realize, wow, there's a lot of different elements. And remember, those are kind of the standard cell library equivalents of the optical devices. Our customers then take thousands and tens of thousands of those optical elements and integrate those into a complex optical circuit there. And they have to know that they're going to work. And of course, these are not 45 nanometer feature size dimensions. These are really large format curved linear shapes with all kinds of unique stress control items that you have to do on there. And because it has both CMOS and optical, the reliability suite that you have to go through is pretty amazing. And I promise you I won't go through these details. On the left side, you see the electrical reliability, which is the historical things that you do both for the front-end transistors as well as the back-end interconnect, stress migration, gate oxide dielectric breakdown, etc. You then move to the top of the center block there, and you see just the optical components. So every one of those things on the blue highlighted circles there, every one of those has a footprint, a power requirement, a performance requirement, and you have to go in and validate every single one of those components, not just time zero performance, but to take it through high temp storage, low temp storage, 2,000 hours of damp heat, etc. All the while maintaining the fidelity of the reliability on the electrical side of it. And then finally, what we call chip package fiber integration is, I now need to put this whole thing together in a package and make sure that the package level stresses, Telecordia 2,000 hours of damp heat, the index matched epoxy that you're using to adhere the fibers into whichever device you're using for fiber attach. It requires a huge amount of effort to be able to get those platforms qualified. We actually qualified this platform about 2 years ago. And what we know from semiconductors is you don't qualify it once and go to sleep. Process variations, line controls, recipe upgrades, throughput enhancements. There's a lot of change that happens on a platform. And we have borrowed from our semiconductor manufacturing for what we call PRM, which is periodic reliability monitoring. Everything that you see on the center and left-hand side, we do on this platform every single month. Every single month looking for signals, and we compare back to the rest of the data and say, are we seeing any reliability drift? Is the Weibull curve different between the end-of-life fails and the infant mortality? Why? What does it trace back to on there? So it's a big commitment of resources for the platform. The fifth thing that you have to get right to solve the economic is cost, 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 cost. And real or perceived, that the perception today is that silicon photonics in a package form integrated into pluggables or CPO is in fact a more expensive proposition. So on the left side, you see reference to OIDA that actually was talked about in our panel yesterday. We need the left side to look like the right side, meaning that the wafer processing represents 75% of the finished bill of materials, not 25%. Now, there's two ways to fix that. I could quadruple my ASP on the wafer sale, but it has a inversely dependence on the volume that we will run. If we were quadrupling our ASP, which I think was one of the questions yesterday that came up. On the right side, you actually see our own internal modeling activity. It gives you a relative basis for understanding the wafer component, the just post-fab processing associated with the bump technology that you have, and then, okay, amortization of the design cost. This is an all-in cost model. And to be clear, a model for CPO compared to a cost model for pluggables, compared to CWDM, DWDM. You have to have a cost model for every single one of these things to actually know what are the drivers and what are the relative components. But there are some pretty clear trends that emerge from it, and you see it. It's the cost per fiber and the fiber bundling that does not have automation today to go configure that to the customer-specific fiber bundle that they're going to bring in. It is for sure the number of optical tests. So optical tests today at the functional level is not measured in wafers per hour, right? It's measured in hours per die there, and we know that needs to come down by 1 to 2 orders of magnitude. So there's a major, major challenge associated with that. And then, oh, by the way, you're doing 4 test insertions at least as a CPO optical module goes through the process on there. And then laser costs, right? So now, you see kind of the HVM cost target we have, and honestly, the only 3 things that moved in there were related to what we know well how to do well today, which is how we're going to be able to amortize volume to pull our wafer costs down on there. The rest of the work is a really big challenge to go work with the rest of the ecosystem. Okay, so that 1 millisecond, you saw what it takes to go from wafer level to a fully CPO implemented with fiber attached to it that I've deliberately blurred out because there's a lot of intellectual property in there. But the point I want to make first and foremost is the process is really complicated. Really complicated. Thermal cycles on laminate substrates, having to protect where your fiber is ultimately going to be attached on there. The point I want to make is it takes, they say it takes a village to raise a child. In this case, it takes an entire ecosystem to be able to put this solution together. The reason you didn't see any cost down on the non-wafer related components on the previous page is we don't have an ecosystem pulled together today where we're all pulling in the same direction. And part of the call to action is we really do need to build ecosystems. For today, I chose to not put all of the logos on there for the ecosystem that GF has, because quite frankly, we still have gaps in it, and we've learned that when a CTO of one of your major customers says, we don't have experience in this space, you guys got to go fix this for us, we're now out embracing every single one of the elements that are in this chart to understand how do we enable our customers with at least 1, if not 2 or 3 partners in every one of them. Okay, so let me talk about what the answer key looks like, and hopefully this is a summary of the points that I've made. First and foremost, benefit from the economy of scale of running this in an operating 300 millimeter facility with all the tool capability and automation that happens. And at least for the wafer processing of what happens today, our 45 CLO customers' products run lights out in our factory with no human intervention once you've actually built the route that the process will follow. The second thing is, my point over and over and over again, everything is going to get better as you ramp volume on here. It is the secret to get the rest of the ecosystem that doesn't exist today looking at sufficient volume to warrant their own commitments and investments that they're going to have to make, as well as the classic learning curve of debugging that entire supply chain. One thing, and it is one of my core messages that I'm going to ask about, is I come from the semiconductor world. I'm on the Industrial Advisory Committee for the U.S. CHIPS. I am doing my darndest to get allocation of that CHIPS R&D that's trying to solve a 2-nanometer nanosheet problem for the U.S. government to allocate funding into silicon photonics, and that's both at the chip level as well as in the packaging ecosystem on there. So a call to action to make sure we're leveraging the EU bill, the Japan bill, and all other forms of CHIPS R&D funding. We do know, okay, we have a path to 200 gig today. By the time we're looking for 400 gig, we know that there's likely introduction of new materials. Automation of equipment, so you heard Ficantech talk yesterday about them going from nowhere to now having a commercial industrialized test platform. All of these things need a huge amount of focus on there. The last point that may result in Jose not inviting me back to this conference next year is, while I love OFC, we had a team at ECOC last week. We're here today. We're very happy to be in this environment. There's a whole other side of the industry called $500 billion of semiconductor that has built ecosystems and has decades of experience driving down learning curves to drive cost, improve yields, et cetera. And as much as I value the opportunity to have a very concentrated interaction with all of you, and thank you for the last 2 days of discussion, made lots and lots of connections, we need to elbow our way into the semiconductor forums. It's starting. You can go to ISSCC, you can go to IEDM, and there are starting to be photonics. We need to kick the doors wide open and come in like we're proud of what we're trying to do and that we're there to leverage everything else that that ecosystem has. So thank you for inviting me to this, but I invite you into the semi ecosystem as well. Thank you.
You are still invited to come next.
Thank you.
So I have a couple of questions for you. The first one is an easy one, nice one, and the second one is a bit more provocative one. Which one do you want?
Take them both.
I'm going to start with the easy one. You said about new materials. What is the roadmap to incorporate new materials to silicon photonics?
Well, so there's a lot of them. We know for modulators that the move out of silicon is going to go into a couple different materials. We have active engagement on thin film lithium niobate. We talked briefly yesterday about quantum photonic computing, which has got a set of materials coming in as well that are alternates to thin film lithium niobate. We continue to look at all forms of 2D materials. So the 2D is probably 8 or 10 years from now at the transistor level on the CMOS technology. We think as that matures that there's a lot of opportunities to harvest 2D materials as well. Okay, now the tough one.
Yes. So with 300 million, you put yourself as the leader worldwide on photonic integration, in my opinion. But I think it's true.
No disagreement. So where's the tough part of this question?
So do you know how much money all these people, or most of them, have invested or gotten invested in the last years to develop photonic integrated circuits? Do you think it's fair? And now you perhaps are waiting to incorporate new materials until these people develop those new materials and you invest a bit and you get them and you become the leader? Is that fair? Is that the future of photonics, to help you being the leader for a few dollars?
Sure. By the way, there's two ways to solve it. One is by making investments in funding. The other one is wafer sales, right? Commercial volume business. And that's, the VC panel that was talking earlier about patience. We actually started this program 10 years ago. And it was a study for a few years while we were figuring out what we didn't know about photonics. But the ramp up of investment, this is, by the way, I'll just tell you. So, we spend hundreds of millions of dollars on research and development on all of those 8 platforms I started with. This is the single largest investment we make, and it's the single largest investment for the 5th year in a row. So we're all in on this platform. It'll take a while for the area under the curve to catch up to the billions that you are all investing in this space, but we're on that journey.
Greg, you've been a rock star these days. You're welcome back next year.
Very good.
Thank you for having us here.
Thank you all.